In our opening example, we found that the general solution to y prime equals 5, negative 2, negative 1, 4 times y, in terms of constants c1 and c2, are given by the equation y of t equals c1 times e to the 3t times the vector 1, 1, plus c2 e to the 6t times the vector negative 2, 1. Let's sketch now the phase portrait using the general solution that we found. We know that the straight line solutions are scalar multiples of the eigenvectors v1 equal to 1, 1 and v2 equal to negative 2, 1. So we'll start our phase portrait with those. Since both e to the 3t and e to the 6t go to infinity as t increases, these straight line solutions move away from the origin, which we'll indicate with arrows pointing away from the origin. But what about curves of other solutions where c1 and c2 are not 0? Starting with some generic point, what happens as t goes to infinity? Well, as t goes to infinity, our function y of t, which is a linear combination of v1 and v2, becomes a larger and larger sum of v1 and v2, because the scalar multiple for each is going off to infinity. Both of these terms are going to infinity, but e to the 6t is increasing faster than e to the 3t, and will be the dominant term for y of t. In other words, y of t is going to behave more and more like a scalar multiple of v2 as our scalar multiple of v1 becomes less and less significant. That is, y of t becomes asymptotically parallel to our vector v2 as t goes off to infinity. And on the other hand, as t goes to negative infinity, y of t is going to be going to 0, since both e to the 3t and e to the 6t will be going to 0. But in this case, e to the 3t will be dominant, because just as e to the 6t was going to infinity faster than e to the 3t, e to the 6t will be going to 0 faster than e to the 3t as t goes to negative infinity. So the term e to the 6t times negative 2, 1 will become less and less significant, and e to the 3t will become dominant. So y of t is going to go into the origin, but it'll come into the origin asymptotically parallel to the vector 1, 1. So we see that this solution near the origin is parallel to 1, 1, and away from the origin becomes asymptotically parallel to negative 2, 1. And again, this argument can be made for any solution where c1 and c2 are not 0. So we'll draw in a representative function in each of the regions bound by our straight line solutions. And this gives us our phase portrait, which is the one that we found using the direction field.